last up today we have Artin from UW, advised by me.
Thanks. Today I'm going to talk about heavy-tailed noise in linear and kernel bandits. It's a recent work with Kevin and John from NUS. So basically in stochastic environments, usually what it's prevalent to assume is that either like rewards or data is bounded or like has a sub-Gaussian behavior. But is it actually what we see in real-world data? It appears to no. Like there are many examples like returns in financial markets or in computer networks, delay of the packets or other things that what we see is actually super Gaussian or even what we call heavy-tailed noise, where the decay of the tail around the expected value is not exponential. It's polynomial or slower than exponential. So we want to be able to like provide ML algorithms that sort of handle this heavy-tailed noise. What we do assume is the minimal assumption that this noise has a 1 plus epsilon bounded moment. So it can even have like infinite variance. So as an example to start, look at multi-arm bandits where we have n arms with expected reward mu1 to mu_n. But what we observe is mu_i plus a noise eta, where eta can be heavy-tailed. And so what does the usual algorithm like UCB does? It does empirical mean plus a confidence bound. The problem here is that when the noise is heavy-tailed, the confidence bound becomes much more larger and suboptimal. In particular, for the empirical mean in here, we have it scaling with delta polynomially, whereas we want, if it was sub-Gaussian, we had this nice Chernoff bounds that it scaled logarithmically with delta. So what we want to do is that to change sort of this estimation so that these algorithms would work. As I said, empirical means is not optimal. So for robust mean estimators, it's actually like really rich subfield of a statistic. There are many different estimators for mean estimation. One simple thing is truncated mean, whereas it says that like if the data is empirically too far from the mean, then we just drop it and then calculate the empirical mean there. This like creates an artificial like bounded variance. Another idea is like median of means, which I assume like many of you are familiar with, and there are many more like more sophisticated estimators, and all of them basically show that when we have a bounded 1 plus epsilon moment on the heavy-tailed noise, then the confidence bound scales something like this, where like when previously we had like escalating with square root of t in the denominator, we have t to the epsilon over 1 plus epsilon here. Going back to and also like this shows that like it achieves actually like the best possible regrets that scales something like this. And so we want to, going back to the problem we're studying, linear bandits, we have that instead of a discrete arm set, we have a subset of RD with expected reward of an unknown parameter theta star. We again have this eta, which is heavy-tailed, and here's the problem. Extending this tight mean estimators to RD is actually not trivial at all, and it is challenging. Many other works have tried to do this, but like, for example, for Huber loss regression or just like generalizing median means to RD, the problem is that it's actually not optimal. It scales something like D, and the correct T dependence, but the dimension dependence is not optimal, because we assume that if we're paying more for the scaling in terms of number of data, we want at least the dimension dependence to get a bit better. And the question is it possible to actually do that? And we answered that it is possible. And so the idea is that, okay, let's sort of use these tight mean estimators by estimating each arm individually in its own direction and then concatenating at the end. So basically this sort of pipeline. where first we change our data to random variables that estimate A transpose theta star for each xi's, and then use a robust min estimator to compute R hat of A for each arm, and then try by like finding the minimum distance theta, finalizing our estimation. This part is basically you could think of it as one-shot least squares, like basically with one data point. And yeah, we sort of show that this scales something like that, which the number of data dependence is again the same, but the thing is that like the important parameter here is this M star, which I'll get to later, which depends on basically the geometry of the action sets and what happens with the 1 plus epsilon noise data there. And
is there a minus sign in that middle expression between the xi and the yi?
Where?
In that expression there.
Here?
Yeah.
No. This is A inverse here. Basically, yeah, A is like the expected A transpose, so yeah.
Yeah, I understand. But I thought you were doing some sort of regression. So you're taking difference between A transpose X.
Yeah.
Y. Okay.
And yeah, basically, so yeah, this is like what the estimator does, and yeah, going to what this M star actually is. And yeah, the thing is that here I assume like there's a distribution, data is coming from a distribution over A. When we're doing bandits, we can actually control distribution. So basically we want to minimize M star here because it's the only term depending on the distribution. And so yeah, this is what M star is. It's a bit unintuitive what actually it means, but to like make it more familiar, if epsilon is equal 1, which is like the finite variance setting, then it becomes the norm of A in terms of covariate matrix, which as those familiar with experimental design, this is equivalent to finding a G-optimal design. But yeah, for epsilon smaller than 1, it becomes a bit more interesting as I get to. Like for some geometry, we see speed ups. And like to think about it, like intuitively in terms of geometry, for epsilon equals 1, we were trying to find a minimum volume enclosing ellipsoid to encapsulate the data set. But for epsilon less than 1, it becomes a minimum volume super ellipsoid. Where yeah, like affine transformation of a L1 plus epsilon ball, basically. And so finally, like what we do is that like we just combine this estimator with this experimental design with the phased elimination. That's adds exponential levels of error threshold. We sample from this lambda design and then eliminate the suboptimal arms. And what we show is that in minimax terms, the regrets scale something like this, which if epsilon is less than 1, then we've improved the D-dependence bound. Yeah, and as I said, the interesting is that because MSR is action dependent, we see speed ups in some geometries. For example, LP normals if P is less than 1 plus epsilon. And this also extends to kernel bandits, where like the dimension is infinite. Basically, in the algorithm design, we don't care about the dimension. It's only M star that matters. And like we show that for matrix kernels, for example, for many parameters, we show that like sublinear regret exists, whereas before we didn't know that it existed or not. Yeah. Yeah, so in conclusion, yeah, what I wanted to talk about in this talk was basically that heavy-tailed revolves fundamentally change the structure of your problem, and if you like don't account for it with different estimators and different designs, then yeah, you can't, you're handling it not optimally, and this even happens like for data that's like start with, for example, there was this work that showed that if even you start with not heavy tail data and you do a stochastic gradient descent, you could end up with a heavy tail distribution. And yeah, there are some open problems. I mean, there are many open problems here. Meaning, the one in the linear case is still there's a gap between the D dependence. We showed D to the 2 epsilon over 1 plus epsilon lower bound for L2 normal, but still, as you see, like there's a gap between these two, and we're not sure which one is tight actually. And yeah, there's also a question of what's the actual like MS star for each geometry. Like we showed speedups for some geometries, but yeah, there's a still question that which geometries actually provide speedups and which do not. And yeah, as a like point in normal stochastic setting, geometries don't matter because of Kiefer-Wolfowitz. And yeah, this is like an interesting thing in case of heavy tail. And in beyond linear case, there's also a thing that like usually the assumption in realizable setting is that we have access to a least square oracle. But here probably in the heavy tails, that assumption needs to be like fundamentally changed because yeah, like for example, access to a 1 plus epsilon minimizer instead of a least squares one. Yeah, thanks.
So when you're talking about the optimal design criterion, right, you have this 1 plus epsilon exponent.
Yeah.
How do you actually compute that? So if the exponent was like 2, we have like Frank-Wolf style algorithms, right?
Yeah.
Do you have any?
So this is this is actually convex, but because epsilon is between 0 and 1, but yeah, basically what you should do is this is always smaller than this norm. So at worst case, which that's what we actually use, is that we could use Frank-Wolf and use a G-optimal design and we get the worst case. But in case of particular geometries, we could just use like a stochastic gradient descent and yeah, find a good solution for it. Yeah.
All right.
Oh wait, can I ask a question? Yeah, wait, so I guess going back to the very beginning, so like the super naive algorithm here is I guess like use some sort of robust mean estimator and then just like do like headed UCD on this thing?
Yeah.
Is there a lower bound for like that algorithm? Like do we know that like that approach like cannot sort of achieve the rate you're getting here?
Which one?
Like the rate you're getting at the end.
Yeah.
With your algorithm, like do we know that this sort of approach kind of like caps out like that it can't get the same rate?
Oh.
Like if you're to do the natural like lin UCB analog.
Yeah. So I'm not sure if like the analysis is loose or not, but those type of algorithms all get D dependence.
Yeah,
like,
I was just curious if there's like an algorithm specific lower bound that shows that it's like tight for those ones or something like that.
Oh no, I haven't seen it,
Okay.
but yeah, that's good.
All right.
Yeah,
So we
thanks.
thank all the speakers now, and then go to a closing session.